Welcome to a new video in the video series on systems biology, digital twins, and AI. So we are now in block 2. We are learning how to use data when analyzing the models. And in the previous video, we learned how to formulate the parameter estimation problem, which is a minimization of a cost function, or possibly the maximization of a likelihood function. Over the parameters. So we're simply looking for the parameters that gives the lowest value of the cost function. So we will now assume that we have this already formulated and that we are about to put this into an optimization algorithms that solves this problem. And there are two different categories, you could say, of optimization algorithms. There is local and global. And in this video, we will look at local optimization algorithms, and the next one we'll look at global. So how to create an algorithm that can find the optimal values of P that finds the minimum value of the cost function and find the arguments, so find the parameters that gives the minimum value of the cost function. So that's what we're doing. And let's have a look. So the first thing is to look at something called the Newton-Raphson algorithm. This is a very, very old algorithm. So Newton is the famous Newton, and Raphson is another guy. And they came up with this algorithm many hundred years ago. And this basically is in a way an optimal algorithm if you can use it, but it might be a bit unstable, and for various reasons you don't want to use it as it is. But let's start with the derivation of that and intuitive understanding of what it does. And then we'll translate this to the parameter estimation problem and compare with another sort of intuitive, maybe the most intuitive algorithm, but that's also much lower, called the steepest descent algorithm. And then we look at some maybe more type of algorithms that you actually use. So they are various approximations of the Newton-Raphson algorithm called quasi-Newton algorithms. And in the end, we look at the Nelder-Mead, which is a derivative free. So here we'll talk about ways to calculate these derivatives, use the sensitivity equations. And then if you don't want to deal with this issue of calculating all of these derivatives, then you can use a derivative-free approach. And maybe the most famous one is called Nelder-Mead, which is still a local but derivative-free approach. Okay, so let's jump in. So we have some kind of function f here that depends on some variable x. So now this is in a very general form. So x here is now not the state; it's just something that the function depends on. And we are at some particular point here, xn, and we have the ability to calculate the function value here. And we want to know how to take the next step. And the basic idea in the Newton-Raphson algorithm is to say, okay, so we know the value of f. We can also calculate the derivative of f. And then once we have the derivative of f, we can just say that, okay, so if the derivative would be the same all the time, and we would move along the derivative, when would we hit the zero axis? So the root, the thing we're looking at is where the actual function is hitting the x-axis. So where the actual function equals 0. That's what we are looking for in the Newton-Raphson algorithm and in a root finding algorithm. So we'll talk later about how this relates to the parameter estimation problem. But for now, we are looking for the 0 of a function. So this point here. And we don't know what the value of the function is along this line here, because we are only here. And to calculate the derivative at other places, we simply need to analyze more places. So this is an algorithm where at one place at a time we do some calculation and then we take a new step. So it's just when we solve the ODEs. And there are actually ways to translate ODE solvers to optimization solvers. So they have lots of similarities and overlaps. We have the function of f, and we can calculate the derivative. And if we assume that the derivative will always be the same, again, think Euler forward, then what would happen? Then let's just step towards where that assumption leads us as the root to be. So if that assumption would be true, the root would be here. So let's step here and let's find this point. So let's make this be x of n plus 1. So then we need to find the formula for that, and that's very straightforward. So we can do it together. So we simply use the definition of the derivative for such a constant linear function as we have here. So it's then simply delta y divided by delta x, and delta y is f of x of n minus the bottom here, which is 0. And delta x here is this value here minus this value here. So xn minus x of xn plus 1. So if we multiply this one up here and we divide by this one here, then we get f divided, and we ignore the 0, then we get f divided by f prime, so the derivative, and here xn minus x of n plus 1. But this is the one that we want to solve for, so let's put this one over here, let's put this one over here, and then we have the formula x of n plus 1, the new step in the space that we are moving around in, is the old place minus the function value divided by the derivative. So this is the Newton-Raphson basis formula. So it's a very short derivation. You can do it yourself in a couple of minutes. So the principle is, to sum up, use the gradient or the derivative if you're here, and step to where that one would cross the line, where that one sort of has f of x equals 0. And then when you're here, you are actually not at 0. So here you will actually have a function value that's not 0. Here you will have a new derivative, and then you would step in the same way in the direction of this new derivative. And here you see some of the reasons why the Newton-Raphson algorithm might have problems if you start too far away. Because here you see that the derivative is almost flat, so it would sort of point somewhere very far away. So this might not be a good idea if the function, if you're starting this far away. So probably this is one of the problems that local optimization algorithms have actually. But if we just make this a little bit nicer, so let's bend it up a little bit and then see how this evolves. Then we will simply see that it starts here. We calculate the derivative. We go here, recalculate the derivative. We end up here. We recalculate the derivative here. And here you see that now we are approaching the optimum very, very fast. So at the end here, you are very, very fast at converging to the true root. So in the beginning, you might have these type of problems, and this is why this is unstable in the beginning. But when you're close enough, it has a very fast convergence. So the number of accurate digits will double each step. So it's very fast here at the end. Okay, so this is the basis for the Newton-Raphson algorithm. Now let's come back to the optimization problem that we want to solve. We want to estimate the parameters. We want to minimize the cost function. And the basic idea is that if you want to have a minimum for something, that's the same as saying that the derivative, or if you are in a higher dimensional situation, the gradient, where that is equal to 0. That's where we have either a minimum or a maximum. So all of the local minima and all of the local maxima will fulfill this property. So if we simply look for all of the parameters that fulfill this condition, then we can use the Newton-Raphson, because this is a root finding problem. Here we want to have the 0. So then that means that the derivative here, or the gradient of the cost function, that's the f from the previous slide. So and the derivative of that, so f prime, will translate to the second derivative, which is called the Hessian. And since this is a vector, this will actually be a matrix. So the Hessian here is called H. So the Hessian of V is what will be translated to f prime. So with this, we are already at basically the standard formula for what this will look like in the case of an optimization situation. So we will see here that it's almost exactly the same as in the previous slide with these modifications. So here we have P. Now we are in the parameter landscape of n plus 1. So the next place in the parameter landscape or space that we want to be at. It's the old point minus, and let's ignore this h for a little while and just look at this one. So this is the Hessian. So this is the second derivative, which equals f prime in the previous one, and inverse. So this is divided by f prime is what this is, and this is f. So this is f divided by f prime. So it's exactly the same, but we have an h here. And so the previous guess is the same, and this h here is the step size. And the step size is there to sort of keep more track of these type of problems. If you take too long steps, if you're too far away from the root, from the optimum, then the derivative might simply be pointing way off. So therefore, typically you want to take shorter steps. But the sort of the default, the simplest option is that it's simply 1, h is 1. But if you want to have a more stable option, typically you take smaller steps. And again, this is very analogous to the simulation of the ODEs, when you also, if you want to have a more stable solution, you take shorter steps. And here there is a word that you should know, which is called trust region. And this is where you, in the same way as in the ODE solvers, where you compare maybe a fourth order and a fifth order Runge-Kutta, here you will compare the actual improvement, which is the cost function, or the thing that you want to minimize, which is actually delta V here. So you compare that value with the one predicted by you taking a step in this direction. So if you take the full step, you predict that it's 0. But if you take a step of 0.1, you predict that it's a reduction of 10%. So if this is not a reduction of 10%, then that's an indication that the derivative has changed a lot along the way, and that in turn is an indication that you should probably take an even shorter step, because this is a sort of very dynamic function. So trust region is simply step size control, where you are making sure that you're not taking too long steps. So the final thing to say here is that this Hessian here, this is very expensive to calculate, because this is a matrix. And for each element in this matrix, you need to calculate the cost function again. So you need to do the perturbation of each pair of parameters. So each element in this matrix is a second derivative with respect to a pair of parameters. So dv, d2v, dp1, dp1 is the first element, and then dp1, dp2, dp1, dp3, and so on. So for each of these elements in this matrix, you need to do a new simulation, to do a new calculation of the cost function. This is very expensive, takes a lot of computer time. So therefore, you typically want to use approximations for this. And this is where we'll get into quasi-Newton algorithms. But before we go into that, I want to show that all of this, just as in the case of ODE solvers, is a sort of trade-off between speed and reliability. So the sort of slowest option is to simply go in the direction of the gradient, so the first derivative. This is stable. You are sort of not trying to sort of find the optimal quadratic convergence, but you want something that's stable. And this will, unlike the Newton-Raphson, which is faster and faster, the closer you go, this has an exponential decay, meaning that it's slower and slower. So the Hessian has a quadratic convergence, but the Hessian and the Newton-Raphson has a quadratic convergence. Here you don't use the Hessian, you only use the first derivative, and this is called the steepest descent. And if you want to have some kind of trade-off between the two, so you want to have the speed to as much extent as possible of the Hessian, so the Newton-Raphson, but you don't want to calculate the full Hessian because that's very expensive, and you sort of want to use various approximations, and also this variable step size. Then you come into all of this sort of modified Newton-Raphson called quasi-Newton algorithms. So let's here just look at root finding. So here is the optimum. This is the 0 point. Now we are in 2 dimensions here. So previously we were only in 1. Here we are in 2 dimensions. So these are the level curves. And if you all the time go orthogonally to the level curves, then you're just going in the direction that locally it seems like it's the fastest direction. But if you also make use of the Hessian, so the second derivative, then you're seeing that this red line here is much faster. So there's a red line here. So the steepest descent is sort of the one with the linear convergence, but this is a faster approach. And here it will go faster and faster. So that's sort of the basis. And now let's just look a little bit at some of the calculations for this type of approximations. So a situation that we very often have in the cost function is that it's formed by this sum of squared residuals. So if you have this particular form here, so R here are the residuals, then a particular form of quasi-Newton, which is called Gauss-Newton methods, they simply take the first derivative and then they take the prime of, or the transpose of that, and you multiply together. So this becomes a sort of approximation of the Hessian. And this is the first derivative only, and these are the residuals here. So here, you never calculate the second derivatives, but this here, which is the transpose of the first derivative times itself, this becomes a matrix. So this is something that you can that is an approximation, and it's of course much faster because you only need to calculate one vector and not the whole n by n matrix. And a special case of this is Liebenberg-Marquardt, where you have this Gauss-Newton approach, but where you also add this trust region. You remember when you have this variable step size and you compare the predicted with the actual improvement. So these are some names that you sort of should know and the basis of what they are doing. Okay, so let's just say something short because we will come back to that also in the next video, which is when you calculate these derivatives, the sort of most straightforward way is to simply do a simulation of y in the original parameter and then in the perturbed direction. So for each parameter I or pi, you do a little perturbation in that direction. So you change the parameters from p to p plus a perturbation in one direction at a time. So here you do 2 simulations and you compare the outcome of those 2 simulations. If you here you need to have a very accurate simulation in order to find very small differences is in simulated outcome. And this might give all sorts of rounding errors, and it is not, and also you need to do this many simulations, because for each parameter you need to do a new simulation. So one other way is to calculate the analytical formula for how the function y depends on the parameters. So here we have the differential equation for that we sort of start with. And then by just using the chain rule, we will differentiate with respect to the parameters, and we will get these equations here. So here we have new states. So we have this S, which is a new state, and you see that the S is simply the derivative of y with respect to b. So this derivative will become a new state that you have a differential equation for. So you will have, for each derivative here, you will have a new differential equation. So here you have sort of a new x, if you want to, which you have the time derivative for, and it depends on itself. And these are the derivatives which sort of make up the differential equation for these new states. So we have lots of new ODEs that where each of these new ODEs describe how the derivative is changing over time. So in this way, you only need to do one simulation for this expanded set of ODEs to get all of the derivatives. And this is another way to get the derivatives, where you expand the set of differential equations and you simulate this expanded set, and then you get all the derivatives for free. And this is called to solve the sensitivity equations, or to do internal differentiation. So as you notice, that there are sort of lots of issues with these derivatives and the first derivatives and the second derivatives. And if you want to ignore all of that, and especially if the derivatives are hard to get by, maybe you have a noisy landscape which is sort of rough and it's hard to get accurate things, then a more robust way, which is not using any derivatives at all, is to use something called the Nelder-Mead. And here you have a simplex. So it's sort of in 2 dimensions, it's simply a triangle. So you will see it here in the beginning, it's a big triangle, and you see it sort of moving around, and then it's approaching. So here we have the level curves again. It's approaching the optimum here. So here we have another situation where we have this triangle that first is big, and it's being transformed in different ways. So you see here the corner went from being here to here. So that's called the reflection. And here you see shrinking, that it's getting smaller and smaller. So you can reflect it. You can also extend it. If you have a good direction, you can make the triangle even more elongated in this direction. You can shrink it, and you can do this type of modifications. So here you have sort of calculated values for each corner in this triangle, which is called a simplex in a higher dimensional space. And this is an option that allows you to sort of move around and find the optimum in a way where you don't have to calculate any derivatives. And this is a commonly used approach. The final thing I want to say, and that leads to the next video, is that in these level curves here, you see that you have one optimum here, one optimum here, one optimum here, and one optimum here. And if you start here, you will just converge to this one. So if you want to reach these others, you have to start in other places. And that's one way to still use only local optimization, is to start in many places. But another way is to use, when you have this sort of many local minima, is to also use a global optimization algorithm. And that is the topic of the next video.